Welcome back to the second part of the webinar. May I now invite Professor Zhu to introduce our next speaker, Professor Xinhui Lu. Professor Zhu, please.
Thank you. So good morning, everyone. It's my pleasure to introduce one of young, energetic, and very productive colleagues in the Department of Physics, Professor Xinhui Lu. Professor Lu is a world expert in synchrotron X-ray scattering, which is a powerful technique to probe into the microscopic structures of matter. So as such, the technique is useful not only in physics, but also for biology, chemistry, material science, basically across all disciplines in science and engineering. Professor Lu applied her expertise in X-ray scattering to study different kinds of solar cells. So by understanding how the morphology affects the functions, the hope is to eventually lead to better solar cells. And recently, Professor Lu is also involved in a major scientific facilities very close to Hong Kong. There's a spallation neutron source in Dongguan, which is about 2 hours from here. It's a world-class facility. And so if you're interested in that facility, you should also talk to Professor Lu. So without further ado, let's welcome Professor Lu.
Hello, everyone. Can you hear me? Okay. Thank you, Professor Chu, for the kind introduction, and thanks to the faculty for giving me this opportunity to share my research and to explore potential collaborations. So, our previous speaker, Professor Yang, raised the land scale of interest to earthquake, and so bear with me. I'm going to reduce the land scale back to angstrom and molecular level. So in nature, we find there are actually a lot of micro structure with complex land scales and formats. So the development of advanced techniques to characterize these interesting structures is highly demanded. So the technique of our group's expertise is X-ray scattering. So there are actually a lot of different variants of X-ray scattering, but the basic principle are very simple. So they are all based on the Sprague's law. So basically, it tells us the length scale of structural order that we are interested is related to the wavelength of the probing beam and the scattering angle. So if we want to visualize the scattering pattern, we have to go to reciprocal space, and then we draw an evosphere. So the reciprocal lattice that is intercepted by the surface of evosphere will satisfy Bragg's law, will become constructive interference and become bright spots to be projected on our detector. So how we choose the probing beam wavelengths and how we perform the measurement, whether in collect the wide angle or small angle scattering, whether we do transmission mode or reflection mode, will determine the key structural information that we can extract. For instance, crystallinity, the length scale, the orientation of the microstructures. So the solar cell that we are doing research in, they are in thin film structure. So here, the symmetry of the structure breaks into out of plane and in plane direction. So in the in plane, since the solar cell, third generation solar cell are mostly fabricated in spin coating, so it has this rotational symmetry, like jellyfish of Professor Hui. So we just use this unique geometry of scattering, so we impinge our X-ray onto the surface of sample with very tiny angle and collect the reflected scatter beam with a 2D area detector. So in this way, we will have scattering wave vector have both components in out of plane and in plane direction. So we can have the structural information in these of this thin film structure. And if we put our detector close to our sample, we are collecting wide angle scattering, which corresponds to small feature, angstrom level feature, like molecular packing distance, lattice constant. But if we push our detector far away from sample, we are collecting small angle scattering. And in the, this reciprocal space, if go to real space, this is relatively larger length scale. We can collect nanometer to about hundreds of nanometer scale. So we can obtain grain size or domain size information by small angle scattering. So in the following, I'm going to give you several examples of how we use GWAX and GSAX to investigate the organic and perovskite solar cell structures. So for organic solar cell, basically people are using organic semiconducting materials, P-type and N-type material. We call this donor and acceptor. We mix them together to form this bulk heterojunction so that we can have sufficient interfaces for the photogenerated exciton to be dissociated into electron and hole. So this bulk morphology of this active layer, in other words, how the molecule, organic molecules pack inside this active layer, and how this donor and acceptor material nanophase separate is key to the device performance. So GWAX and GSAX are ideal to probe these two different length scale information. So the first example I'm going to show is how can we use GWAX to understand the molecular packing of non-fluorine acceptor. So this is a collaborative work with Professor Zhang Xiaowei in Peking University. So basically his group proposed the very first high efficiency non-fluorine acceptor, ITIC, in 2015. So in this work, we pick ITIC and another similar molecule. So you can see the backbone, they are the same. Only difference is on the side chain. ITIC has a benzene ring on the side chain, but ITIC-TH has a cyphene ring on the side chain. So we're trying to use GWAX to understand the molecular packing common feature of this non-fluorine acceptor to achieve high efficiency. So here is the GWAX pattern of ITIC-TH. You can see if this peak on the QZ axis, this corresponds to the pi-pi stacking. So the pi-pi stacking of the conjugated backbone is relative small feature, so it appears at large Q, and then lamellar stacking peak corresponding to the conjugate backbone separated by the side chain, so in this A direction. So when we see lamellar peak in the QR axis and pi-pi peak in the QZ axis, we know the orientation of this molecule is face on, not edge up. Okay? And then in the in-plane direction, we find another group of peaks which are located at different Q, and they're also up to fourth order. So that means there exists another long-range structure order in the in-plane direction. So we guess it is like this. So it is the backbone order due to the end group pi-pi stacking. So we can extend the structural order in the C direction. Okay. So then our hypothesis is further confirmed by the scattering pattern of ITIC, which has exactly the same backbone. So we can observe the backbone peak at exactly the same Q position. Although the crystallinity is lower, but it still, you can see the first order diffraction peak. Okay, so confirm this structural order. And then we try to enhance this structural order in the bulk heterojunction. In the binary film, we do not see the backbone peak, but in the ternary film, we can gradually tune up this backbone order by changing the mass ratio of ITIC and ITIC-TH. So since these two molecules have exactly the same backbone, so they can have mutual stacking of the end group. And So then we can gradually tune up this peak. Okay, so finally we can correlate this structure order with the device performance. So in collaboration with Professor Zhao Ni in EE department in our school, so we are able to get the in-plane electromobility, out-of-plane electromobility, and we also fabricate the solar cells. And we find the in-plane electromobility is almost an order of higher magnitude of higher than for the ternary cell than the binary cell. Okay, so that means this backbone order indeed form a long-range electron transport pathway to facilitate the electron transport and improve the mobility. So the second example I want to show is how we use small angle X-ray scattering to study the nanophase separation of the organic bulky junction. So the conventional technique is can only reveal the in-plane nanophase separation. The out-of-plane structure is shadowed by the unit peak, which is due to the reflection and refraction effect. So here we just slightly change the experimental geometry by still using Grazing incidence, but collect the transmitted scatter beam from the front edge of the thin film. So we call this technique GT-sex. So by doing this, we can produce a very nice, beautiful, symmetric scattering pattern below the horizon. Okay. So then, when we apply this technique to the bulky junction, we can simultaneously obtain in-plane and out-of-plane nanophase separation information for the first time. The last example I want to show is how can we use in situ GWAX to understand the perovskite crystallization pathway. So perovskite solar cell is another solar cell which is very hot recently because the efficiency is above 25%. So the structure is well defined, much more well defined than the organic solar cell. Basically, it is this lead halide 6 octahedral shear corner form cubic structure, and then we insert a large cation into this cage so that to stabilize the cubic structure. But if this size, the egg side cation is too small or too large, the cubic structure will collapse. Okay, so we are trying to mimic the fabrication condition, like spin coating, drop the anti-solvent, and spin coating and annealing to observe the crystallization pathway of this perovskite solar cell. So here is two videos to showing two systems, one with cesium, one without cesium, and you can see how the GWAX pattern evolve, and they are undergoing very different crystallization pathways. Then after we go into the look into the detail, we can see for the system without cesium, it is undergoing 3 stages of crystallization, and for the system with cesium, it only undergoes 2 stages of crystallization. So in collaboration with Professor Zhu Junyi in our department, they performed a DFT calculation to help us to understand this distinct crystallization pathway and find that actually the incorporation of cesium will lower the formation enthalpy of the perovskite and promote its formation in the stage 2. Okay? So then after we correlate it with the device performance, we find that the duration of stage 2 is actually the annealing window to get a decent device. So if for the system without cesium, the annealing window is very short, but for the system with cesium, it's significantly elongated, and it can increase the reproducibility of the device. Okay, so after these examples, I hope I convince you that X-ray scattering is a powerful technique to understand the microstructure. So you may wonder, where can we do such experiment? So we actually have quite a few scattering facility around. So we have an in-house GWAX and GSAC setup in our department. But the in-house beam is not bright enough. So if you want to perform in situ or GT-SAX measurement, you have to go to nearby synchrotron in Taiwan or Shanghai. And you can also go to Dongguan for neutron scattering, which can give you some unique information that X-ray scattering cannot cover. And there are also some fourth generation synchrotron is under construction or under planning. So that means a lot of opportunity is on the way. Okay, so finally, I want to briefly discuss the project. I'd like to.
Left.
How many? 2 minutes.
1 minute left.
Okay, so I will make it short. So I'd like to investigate the degradation of organic or perovskite solar cell. So why this is project collaborative CRF, because we want to gather expertise in computational simulation, material synthesis, and device engineering, and we're trying to understand the degradation mechanism and how can we solve this degradation to push this field to the real application. Okay, and also if you have any things, this technique can apply to many different systems. So if you have any interesting system or phenomenon that you believe it is related to the static and dynamic structural information, welcome to discuss with me. Okay, that's all I have.
Thank you, Professor Liu. We've got some questions from the panelists. The first question is that, is the inversion of scattering pattern to get the structure always unique? The second question is your Perovskite synthetic? Perovskite is the major mineral in lower mantle formed at ultra high pressure and temperature. And the last question is, are you interested in working with protein? Professor Liu, please.
Okay, so thank you for the question. So let me see. So for the perovskite, actually it is named after its crystal structure. So it's not the natural. We think synthetic by the different ionic precursor. Okay, so this is they share with the same crystal structure as the. So where is the? Okay, so what can I see the question? Actually, I cannot see the question.
You may click the chat button. It's on the top of your screen. Or I can repeat it verbally. The first question is that, is the inversion of scattering patterns to get the structure always unique? And then
actually, excellent question. So, no, the answer is no. So we have to guess. Okay, so based on the scattering pattern, there can be more solutions, and we have to make different samples to confirm our guess. Actually, so this is hope I answered this question.
Thank you. And the last question is that, are you interested in working with protein?
Yeah, of course, yes. So yeah, I think there's a lot of application of X-ray scattering in the biology study. So if you can crystallize the protein, or basically this is to probe the electron density distribution of the sample. So it's not necessary to have very well-defined structure, but we can see, even in a solution sample, we can see the structure, okay, electron density distribution of the sample. Yes?
Thank you. We've got a new question. The first one is, how do you distinguish between long-range and short-range orders by X-ray scattering? And the next one is, what can you do with neutrons that you cannot with X-rays? Professor Liu, please.
So I think I cannot. So the first question is,
how do you distinguish between long-range and short-range orders by X-ray scattering?
Long-range and short-range order, right? Yeah. Yes. So basically, so it's a Bragg's law. Okay. So it's a D that. So we. but if based on the scattering pattern, basically where the peak appears, the structural order that we detect is 2 pi over the peak position. Okay, so it's just reciprocal. Yes.
All right. The next question is, what can you do with neutrons?
With the neutrons.
Yeah.
Yes. So neutron, you can. So basically, the interacting mechanism is different from X-ray. X-ray is probing electron density distribution, but neutron is a neutral atom. So I think the unique part of neutron is it can have very different scattering cross-section with atoms. So for X-ray, the scattering cross-section is increased with the atomic number, but for neutron, it is very sensitive to light atoms like hydrogen. So it has a lot of application in biology and organic materials. And it also have spin and magnetic moment, so it can investigate magnetism.
All right, thank you, Professor Lu. And let's move on to the next talk. May I now invite Professor Zhao to introduce our next speaker, Professor Eric Zhong. Professor Zhao, please. You need to, yeah, can you hear me now? You need to unmute your mic. Okay, it should be working now. Yeah, it's fine.
Okay, yeah. Okay, good morning, everyone. So, just a moment. So let me, okay, so I can hear myself, yeah. So it's my honor and pleasure to introduce my colleague, Professor Eric Zhong, in Mathematics Department. Professor Zhong received his bachelor's degree and his MPhil degree, both in our department, and then obtained his PhD from UCLA in 2005. After his PhD, Professor Zhong was a visiting assistant professor at UC Liwen, and then from CAM and instructed in California Institute of Technology. He joined our department in 2008. Professor Zhong's research interests are extremely broad, covering quite many fundamental research directions in applied mathematics, computational mathematics, and scientific computing. In particular, he is a world-leading and the most productive expert in multi-scale method, numeric upscaling, and machine learning, mostly with applications for coupled flow and transport in heterogeneous, porous, and fractal media. Most of Professor Zhong's research are directly motivated and widely applied in many scientific and engineering disciplines, including material science, geoscience, subsurface flow, energy recovery, filtration, and geoscience. Professor Zhong has already 150 SCI ranked journal publications. So that's an average of 10 publications every year after his PhD. This makes Professor Zhong to be the most productive mathematicians in Hong Kong. Based on the rank of Web of Science, Professor Zhong has been among the highly cited mathematicians in the world. Professor Zhong is also a very active organizer of international academic activities, the editorial board in several international applied mathematics journals. Professor Zhong's research is highly recognized by the community. He's a recipient of the Young Scholar Award by Hong Kong Mathematical Society and has been invited to be plenary speakers in quite many major international mathematical conferences. In this seminar, Professor Zhong will talk about data-driven computational techniques for flow and transport in heterogeneous, porous, and fractal media. Please, Professor Zhong.
Okay. Okay, good morning. Thanks for the introduction. And also thank for the faculty for giving me this opportunity to talk about my research. So first, let me start with the three pillars of science, and they are experiment, theory, and simulation. And in order to do simulations, we require some good computational techniques. Let me also here copy part of an article from this magazine, which says that computing has evolved to become the third pillar of science. And this expert also says that computation is not just an extra tool, it's a new way to do science, and it will change how scientists learn, experiment, and theorize. So, so before I talk about my works, let me mention some importance of computational techniques. So I will focus mostly on flow and transport problems because these arise in many applications. Advanced imaging techniques produce a lot of high resolution images about the pore size and geometry distributions in the medium. And it is good because it provides a lot of information, and it will create a lot of interesting properties about the flow and transport patterns. However, this will be very difficult to compute because the complexity of the flow and transport pattern. And that's why the development of accurate and efficient simulations are challenging. And let me mention that a good computational technique can help engineers and domain scientists to make predictions and help them in designing production or business plans. Then let me give some examples. The first one is geothermal energy. As you can see in this figure, so we typically inject some cold water into the underground medium, and then hot water will be produced on the other side. And typically for this problem, we will have to consider flow of water and other substances inside this type of fracture media. And as mentioned by Professor Yang in his talk, the simulation for this type of problem is difficult due to the complexity of the fractures and also the porosity. And another example is unconventional oil and gas production, and it's also very popular in these days. As you can see in this figure, we also typically have to inject water and other substance inside the subsurface region of the Earth. And then typically, and then this water and substance will flow through this type of fracture media, and then oil and gas will be produced. And it's again mentioned by Professor Yang's talk that in the production of unconventional oil and gas, it can create some damages to the environment. So that's why it's important to understand the consequence in this production within a computer before we actually do the production. And another example is filtration. So typically so this is an example of flow and transport through porous media. So typically we have some substance flow through porous media like this. And there are also a lot of applications related to this. For example, in the design of filters, and in the design of water treatment properties, and also in the flow of blood through the artery walls. So these are examples of flow and transport through porous media. So, and also in the design of electric cars, so as you know that the battery is the most important part of these electric cars. And in this application, we also face flow of chemical substance through porous media. So that's why it will be good to understand how the flow behave within a computer. And this will help a lot in the design of batteries. And the final example is carbon sequestration. And this is the process of storing, for example, carbon dioxide underground. And in these applications, we will have to face multi-phase flow problem. And again, it will be very important to design computational techniques to simulate this problem in order to better understand the process. So the goals of our research is to design accurate and efficient computational techniques based on recent advances in mathematics. So what we will do is to produce sophisticated multi-scale model reduction techniques, and this will give coarse-scale equations instead of fully resolved equations. And this means that we only compute the physically important quantities instead of computing every details of the problem. And the motivation of this is to give fast simulations. And the next point is that since for some applications, we may have some measurement data or experimental data, and it will be good if we can incorporate these kind of data into the construction of our computational model. And we actually will do this in the context of machine learning. So what we will do is to use this data to learn the computational models. And we think that our computational techniques can give a beneficial complement to theories and experiments. So let me mention some key ideas of the research. So on the left-hand side, you see that there's a box complicated mathematical model for applications. So of course, this model can be very complicated, and if we just apply classical way to solve the model, it will be very time consuming and also computational memory consuming. So that's why we do the following. We, instead of using this complex model directly, we design a multi-scale reduced model. So we call this multi-scale because for most practical applications, so it will contain a lot of scales, for example, length scales, time scale, and it could be other scales as well. So that's why we call this multi-scale. So we will build this multi-scale reduced model based on some mathematical ideas and principles. So here I list some key ideas over here. So first, we will first identify cost variables. So this means that we have to know what type of quantities we want to compute, okay, instead of computing everything. And the second point is that, so after we decide the cost scale variables, then we will do the computations. We compute the macroscopic parameters, and in order to build our cost scale model. And if we have some measurement data or experimental data, we can also add this data into our computations and learn the macroscopic parameters using some type of machine learning technique. So this computation we only do once for our model. And then we can use this model for various input and output. And this step will be much faster than doing the original model. So next, let me give you an idea of what we do. So here I present an example of two-phase flow and transport. And here we take a SPE10 benchmark permeability, and this is the figure shown on the left-hand side. And this is the equations that we solve, and it contains the saturation, pressure, and velocity of the flow. And then on the right-hand side, we present the saturations of the water in this case. And as you can see on the right-hand side, we obtain this figure, okay, which is 97% faster than traditional method. So let me mention the proposed CLF project. So I would suggest that we could design data-driven computational techniques for applications. Here I did not specify the one specific applications because there are a lot of applications that we could explore. And in order to do this, we will need expertise from colleagues in the science faculty. For example, we can provide our expertise in the design of computational techniques. And we also need experts from physics, chemistry, or biology to give their ideas for practical applications. And of course, we also need experts from statistics for doing good machine learning. And I hope that this will be a synergistic collaboration among the colleagues in the science faculty. And the goal is to produce the cutting-edge simulators for practical applications. And maybe this kind of simulators can be used to apply for some patents, or it could even perform some simulations for COVID-19 if possible. So finally, I was told that I have to include a track record of myself. And since Professor Zhou Jun has mentioned this in the introduction, so I will not repeat this over here. So with that, I'd like to thank you for your attention.
Thank you, Professor Zhong. We've got some questions from the panelists, and the question will be projected to the share screen now.
Oh, okay, thank you.
So the first question is, how transferable are such computational models? Suppose you train your models with data in Asia. Will such models be applicable in South America? The second question is that can the machine learning deal with inputs that are outside of training sets? What are impractical applications such as cosmological or astrophysical simulations? Professor Zhou, please.
Okay, thank you. So for the first question, so I think the idea is that our computational models is highly transferable, because what we do is that we, of course, we solve a lot of different applications, but they have some common features in terms of the mathematical equations and properties and so on. So what we do is that we take the so since there are a lot of commons in terms of mathematics, so we can actually do this and then apply our computational model for various applications. And about the data, of course, if we only collect data in Asia, so the answer is that so unless there was some similarity between the data in Asia and the data in South America, I would say that so this data part may not be applicable, but the computational model part is applicable because the common part is the mathematics. So for the second equation, the answer is yes. We have done a lot of testings, and actually it performs very well when the data is outside the training set. So for the third question, so the answer is so I don't know. So that's why it would be very good that if we can combine expertise from experts in the science faculty. Number 4 is I would say yes, given that we can formulate this problem in terms of a mathematical model. So once we are able to formulate this, for example, chemical reaction in terms of some mathematical models, then our expertise in the design of computational models and also machine learning can be applied.
Thank you, Professor Zhong. We've got a question from Professor Yang. Professor Yang, please.
Hey, Eric. Great talk. and very pleased to see that you are also interested in this fracking and also CO2 sequestration problem. So you have shown the model of your computational results. Is that purely synthetic model, or did you try to compare with any observations?
Oh, so the example that I show is SPE10 benchmark case.
Oh, benchmark case. Okay.
Benchmark case. So it's typical benchmark problem in petroleum engineering, and the problem that I solve is a two-phase flow which contains water and oil.
Okay. Well, I hope you'll be interested in trying your model in some real data set, and then certainly we can collaborate on that aspect.
Yes, that would be very interesting. Yes.
And also another point is that I forgot to mention actually during my talk, and then we are also actively using machine learning in different aspects. So this is also a message for other faculties as well. So basically, if you're also interested in machine learning, then there's also something we can possibly collaborate as well.
Yes, certainly. Yes, I think what I do has a lot common with what you did since I saw your talk.
Okay. All right. Thank you very much.
Thank you, Professor Yang. For the unanswered question, please send email to Professor Yang. The email address will be shown in the chat room. So may we now invite Professor Yang to give an introduction for our next speaker, Professor Aito. Professor Yang, please.
Okay, thank you very much. Hi, everyone. It is my pleasure to introduce my colleague, Professor Aito. Professor Aito received his bachelor degree in chemistry at CHUHK in 1999. In 2003, he obtained the PhD degree in the same department, where he worked on light scattering and polymer interaction in solutions. In the same year, he received Culture Fellowship and moved to BASF at Germany in 2003 as the postdoc fellow for 2 years, working on colloidal on surface chemistry. After a short postdoc training in the chemistry department at University of Minnesota in 2005, he joined the chemistry department at Chinese University of Hong Kong in 2006, and later on he was promoted to full professor in 2017. Professor Ai is also now an assistant dean in research of the Faculty of Science at Chinese U, also a fellow of Royal Society of Chemistry. His current research interests center on colloidal particles, surface chemistry, polymers, and soft metals. His research has various applications. For instance, he applied the technology in single particle force and fluorescence microscopy to understand the nano-functional structures, dynamics, and biomolecules interactions. Professor Ai also has a number of collaborative projects with BASF, which is a German chemical company and the largest chemical producer in the world. In the talk today, Professor Ai will discuss colloidal particles at interfaces. He is seeking various collaborators, in particular theoreticians, material scientists, chemists, food scientists, and biomedical scientists, in order to expand the applications. Without further ado, let's join me to welcome Professor Ai.
Okay, thank you for Wildvite's nice introduction. Can you hear me? Yes. Okay, so it's my great pleasure today and then to take this opportunity and then to introduce some of the research in our group. And then I hope after this short, brief introduction, and then we can have the more discussion among the faculty members. So my research topic mostly focus on the colloidal interface of science. So this you maybe seems a very old topic, but actually they have many applications we are used currently, like the clothing, and then also a lot of the personal care product. Okay? But one thing you may unfortunately currently maybe this colloidal science they have been fully covered under this nanotechnology. So currently maybe mostly we are mentioned a lot of like the nanoparticle, nano emulsion, and then actually all these are the under the category of the colloidal. So now let me have, give you some of the topic what we are interested. The first one, we are looking for these nanoparticles when they are trapped at this oil-water interface. This phenomenon, as actually you can see, has been reported more than 100 years ago, but it was until 1980, and then the Perovskite had provided a qualitative description of the thermodynamic of the nanoparticle at the interface. So that means there are many parameters can affect this behavior. One thing I want to point out is when the particle trapped at this oil-water interface, and then if you want to detach this particle, basically the energy is closely related to the size of the nanoparticle. And then since that the tracking of this colloidal particle at the liquid interface also become one of the model system people to look for some of the two-dimensional functional material. One of the reasons because the particle sometimes you can see under the microscopic, so you can mimic the, like the atom and how they interact and then packing at this oil-water two-dimensional interface. And then also some of the interesting particle layer, they can be formed at this oil-water interface, and then you see some of the specific electrical or some of the optical properties. So now, because we need to look at this particle moving, so far there we are focused on the particle in the micrometer. So the question is, when we move to the nanoscale, and then this detached energy will be quite similar, like the thermal energy, and then so can we have this property interconnect between this micro to nanoscale. The other question also very interesting when you look at this interaction of the particle trapped at this oil-water interface. So actually they are very, very unsymmetric. So you see if you have charged species, so you can see only have a charge of free ion there in the aqueous phase. So this one you can wondering, okay, how this long range interaction they come from, and then how they can be interact or control the packing of this nanoparticle at the interface. Okay, so we can move forward. So now thinking about what will happen if we have some anisotropic particle when we are trying to trapping at this interface, another nano rock, nano diamond, or even nano dish. Okay, so maybe when we have this control or some of the packing of this material at this oil-water interface, can we have some specific or other kind of the special property generated from this packing of this anisotropic? So this two-dimension can also be extended to the three-dimension if we consider some of the curved surface. So we can also work thinking about we use one kind of the particle. Also we can see or the binary particle, one is bigger, the other one is smaller, and then in other case, one is hard and the other one is soft. So I think the previous Professor Jung maybe also the modeling can help us to understand of this different particle with the different surface property, and then how they are packing from the two-dimensional to three-dimensional interface. Okay, so now let me show you some of the topic we are working related to the materials derived from the particle at the interface. So I think currently in the summer, so mostly I think we use the sunscreen products. In the sunscreen products, there are two filters. One is physical filter, the other one is chemical filter. And then for the physical filter, like titanium dioxide, apart from the nano safety issue, so one particular disadvantage is that means if we use a lot of this titanium dioxide or zinc oxide, after you coat on the skin surface and then you have some this white mask, and then so the customer may not like of this one. And then for the chemical filter, they are mostly conjugate organic compound. And then the consumer will be worried about the penetration into the skin. Or also we have some of the under the sunshine, can they generate some of the phototoxic substance. And then so actually you see in some of the government, they already banned of certain kind of this chemical filter that can be incorporated in the sunscreen product. So look at this question, actually Dow Chemical have many years ago, they already used a two-step polymerization to produce one we call the polymer hollow particle. So you're wondering why need hollow particle, because of the hollow particle inside is air. So you have this contrast difference between the inner core and then the shell. So and then in this way, when you input this one, you can try to replace or some of the physical filter, because this hollow particle, they can also have a strong scattering of this UV light. But I think currently we know this is a polymer based, and then currently because of this microplastic and this kind of the material may become one of the issue. Okay, so in our group, we can also based on this particle at the interface, we can sell a sample of this silica particle at the interface, and then we can lock them together and then to form this hollow silica based particle. And then why we interested in the silica, because when you look at this marine diatoms, their shell actually is also silica material. Okay, so in our group, we can produce different size from the micron to nanometer. But the question is, when we try to incorporate this hollow particle, so what will be the optimum size, or what will be the optimum shell thickness? Okay, so when I look at this question, so actually there are long time ago, people already have talking about some of the scattering of this hollow sphere. So I guess maybe like the Professor Lu maybe can contribute and then give some more advice of this atom, of this item. Okay, and then also actually some of the cosmetic company also they try to incorporate of this chemical filter into this physical filter, and then to see whether they have the synergetic effect. But the other issue may be also some of the environmental expertise they maybe contribute and help to understand whether this will be good or bad, or we have some unknown issue if we have such kind of material. Okay, so if you see, if we don't remove the inner oil inner phase, this is also one of the typical cathode. So when you look at the cathode, first idea you may see you can incorporate on the drug. Okay, but for me, maybe if we want to have the even from the bench from the really become a drug, there is a huge gap in here. So now so I'm thinking whether we can change that direction. We do some of the delivery of some of the in the food formulation, like some of the nutrients used in the food formulation. The idea is that because apart from the many inorganic or organic particles, we can also have many less neutral particles like the gelatin, starch, or thin product. Okay, so in our group, that means we can also try to use this particle at the interface. We can form here. We can form the double shell. That means double emulsion system. So now, why we interested in this double shell? So one thing we may be we are imagining maybe this with this structure. That means they maybe have a long time for the protection and then the control release of some of the active ingredient when we use in the food formulation. But this one we also need some of the expertise to give us some of the comments. So this particular structure, they can be also maybe thinking about how we can use this double emulsion, and then we can try to make some of the heavier food. Because in the many of food, actually it's also this emulsion system. That means ice cream, the salad, and then that means if you eat this kind of the food, that means you have a lot of the fat material inside. But if we change, replace some of the fat with some of the water, that means we make this double emulsion system. So this is maybe the one approach, and then we can you take in the same amount of the food, but the fat, the content will be dramatically reduced. So now that means if we can have some of the system, like here we use some of the natural particle, and then if we can formulate of this like this double emulsion system, this is an opportunity, and then we can be incorporate into some of the food formulation. Okay. And then apart from the hollow and also this cathode, and then also recently we are also interested to have some of this catalysis in the oil water interface. And then particularly if you have some of the reaction, and then you need there to be conducted in two different phases, like one is in aqueous phase, the other one in the oil phase. So I believe this particle, the interface, they can produce, you have a large interfacial area, and and then we have some of the high performance catalysis. For example, we have tried to incorporate some of the enzyme into the soft hydrogel particle, and then we can assemble the particle, hydrogel particle, with the enzyme to this oil-water interface. And then now you can see for this kind of system, and then we can have the catalyst is much higher than the conventional biophase system. So this particle at the interface, actually they can also be very easy to be recycled. So one example we have demonstrated with some of this gold nanoparticle immobilized to the protein particle. And then when we have immobilized or assembled this particle at this oil-water interface, and then we can also have some of the conduct some of the catalytic reaction at this oil-water interface. And then the system is also can be very easily to be recycled. Okay. So that means, so not only for the one-step reaction, this one may be also be possible to have to carry out one pot for multiple step reaction. So one example we saw recently, so this we also use the gold nanoparticle immobilize onto the protein particle. And then later on, and then we assemble this protein particle at this oil-water interface. So now we demonstrate one example. I mean, we had the glucose in the aqueous phase, and then when they have an enzyme, and then when they produce this hydrogen peroxide, and then when this hydrogen peroxide they move close to this interface, and then with the gold as the catalyst, and then they have some of the reaction. The second step reaction will be happen at this oil-water interface. So this is
2 minutes left.
One pot reaction, and then we can be conduct at the same time. So now you can imagine, I think many of the our colleagues in the chemistry department, they maybe have a lot of the system, and they maybe can talk with us some of the interesting this cascade reaction or some of the biomimic cascade reaction, and then maybe we can try to test at this oil-water interface. And then also, I think we also need some of the colleagues help to understanding like the diffusion process between the reactant, intermediate, or product. Okay, particularly they are distributed into different phases. So I think the last example I want to show is the not only we are working on the liquid-liquid interface. So this system can also be extended to the air-water system. To simply, apart from the disperse oil phase or water in oil, we can also disperse the air in the water like the foam. So this foam material, so actually can also be injectable. So I think so this kind of material maybe one of the way we can try to fix or some of this foam defect. And then now you see after we made the foam material, after the setting and drying, so you see they form the theoretical porous material. And then I think this is maybe also if something can be we can use in like the filtration or even in the tissue engineering. Okay. So I hope okay, this is the topic I want to bring out, and then I hope okay, the different colleagues from the different units, if you are interested, and then you'll be and then you can call me, and then we can have a further discussion, and then whether we can say one of the CRF project. Okay. Thank you for your attention.
Thank you, Professor Ai. We've got some questions from the audience, which is showing in the screen sharing. The first question is that shouldn't there be some dependencies on the shape of the particles as well? The second question, are the current sunscreen products safe to use? And the last question, can the nanoparticles be updated by cells?
For the first question, so I think they should be, yes, they should have some of the shared dependent. Yeah, that means because you have, so that means we have the unsymmetric particle, they have you have a displayed different property with the normal sphere particle. For the second question, are the current sunscreen safe to use? Sometimes I think these are still under the highly debate. Sometimes it will be depending on the size of this physical filter or what kind of the chemical filter they can be incorporated into the product. A different company, they may be used different formulation. So the third question, there's nanoparticle. Yes, for sure. They don't also depending on the size, but I think mostly if the particle size less than 200 nanometer, they can be very, very easy to be uptaken by the cell.
We've got a new question. How do the hollow particle size and shell thickness affect the light absorption and scattering?
So regarding of this question, so I think the currently we don't, but the company, some of the commercial products normally now we have the hollow particle size is around 300 to 500 nanometer, and then the shell and then the shell thickness is around 100 nanometer. But I think they maybe depend. This is maybe some of the scattering. I think the size will be affect the scattering. Some like the micron, you have a mild scattering. So I think that this is the one question we need some of the expertise in this field to contribute. Can help us that even maybe some of the calculation or some of the scattering experiment to support what will be the optimum size if we want to scatter the UV light and also in certain kind of region.
Thank you, Professor I. As there's some time left, may I know if there is any question from the panelists? You may put up your hand or use the raise hand function to let us know. There's one question from the audience. How about the mechanical properties of the foams, degradation rates?
I think currently we can tune the mechanical property of the foam, but because we want to, currently we have some of the collaboration with some of the clinical persons, particularly in the tissue engineering. So nowadays we can have to tune the mechanical property compatible to our bone. And then the degradation rate is also controllable, but so far our material is too fast. So we are still tuned of the composition and then try to slow down of this degradation rate of our material.
All right, thank you, Professor I. If you have any question from, if you have any further question or you want to contact with today's speaker, the speaker's contact will be uploaded to the Faculty Research Day webpage shortly after the webinar. So may we now invite Professor Jiang to give closing remarks for us. Professor Jiang, please.
All right, thank you, Andrea. Good morning, everyone. Okay, first, I would like to take this opportunity to say thank you to all the 6 speakers, okay, for the excellent talk. Actually, personally, I have learned a lot. Okay, but I also know that many of the speakers, they have excellent track records. I count the number, maybe 3 of them have over the past 5-6 years have 100% of success rate in the GIF application. Right? So normally, after the talk, or maybe before the talk, the faculty would prepare a souvenir, right, for each speaker. I think this year, we should have some souvenir for the speakers. Okay, otherwise I'll provide it by myself, okay? All right, so thank you again. I think based on all this talk, I think that right now, at least we have sort of 6 potential CRF, right, proposal in the coming years, right? So if you have some idea, have some suggestion, if you want to join some team, please write down the email, okay, write to the speakers. Okay? Or you want to come up with your own CRF, you also can invite some others to join your CRF. Okay? And also I would like to thank the unit heads for their support for this research day by nominating the speakers, also by introducing the speakers, right? And also, I do have a little observation. I count the number of participants, okay? So in the peak hour, there were 160, right? Right now, I think the number is 125, right? So it's really number for the Zoom meeting, I think it's much higher than the in-person symposium. That's maybe at the plus side for the Zoom meeting, okay? I think last, I really want to take this opportunity to say thank you to the supporting staff from faculty office. In particular, Angela, you know, she has done a great job. Also, Jackie is also behind all the things, okay? So that's, I think, pretty much I want to say. Thank you again. Right now, I will also open the floor for all the colleagues who want to have some additional comments. Please feel free to say a few things. Any comments from the panel, from the faculty? I think the one thing I would like to remind is that NGAI is going to organize another Zoom meeting on the topic of solar impact case. So NGAI, you want to elaborate a bit?
No, I think we discussed before with Angela. So now we try to see how's the response of this research day using the Zoom. So now I think it looks quite very successful. I think we see a lot of attendance in this meeting. So maybe I will discuss with Angela and then Lance later. And then so basically we planning to invite some of the professors in our university, and then they had experience in open the company. So I think maybe some of our colleagues may be interested. Okay. How as a professor at the same time, then you can try to set up the company, and then what the difficulty, the challenge, and then so maybe I will try to invite 2 or 3 the colleagues, and then come to, and maybe not like we'll have the formal the PowerPoint, mostly we have some informal sharing, and then like open discussion, and then ask the question from our colleagues.
Right. Any further comment from the unit head or our new dean, Professor Song? Yeah.
Thank you, Liwen. I have thoroughly enjoyed this whole morning. I would like to thank you, all the speakers, for presenting. It's a very interesting and also exciting research. I was very pleased to note that despite the broad range and in the 6 different units in the science faculty, we actually have some consistent themes that actually cut across multiple disciplines, and looking at the presentations and also the interconnection that as an audience we can see. For example, the development of both analytical and mathematical and statistical methodologies, and the development of analytical and experimental measurement techniques, and the applications from geological system to energy system to biological system and to catalytic system and chemical systems. I actually was very, very happy to see there are huge potential for collaborations across the disciplines, just judging from the presentation this morning. I learned a lot, as Professor Jiang said, that I thoroughly enjoyed the learning this morning. I've taken quite a bit of note this morning, and I actually would like to have individual discussion with our speakers later when I have the opportunities and to learn more. I think if we have more discussion among our faculty members, and this certainly will be helpful in our preparation for the next round of the collaborative research proposals, in addition to the general GRFs. The methodological development certainly is not limited to the application that we heard today. Well, for example, Ying's presentation is wonderful. I did not realize our statistical research can actually be brought up to such a level to the single cell and to the biomedical and to the life science. And that becomes immediately apparent in the next 2 presentations. And so this is truly wonderful. I feel so excited. I feel like standing up and jumping and dance with everyone for this type of great research potential. So I'm very happy to see that and looking forward to see more development and particularly collaborative discussion among our faculty members to plan actively forward for the next CRF, both with insight and potentially involving outside researchers, outside the science faculty, and for that matter, even outside the CUHK if it's relevant to help us to moving forward. So that's my preliminary comment. I want to thank you, the team led by Liwen and Angela and Jackie, for the hard work to preparing for this. And I'd like to thank all the speakers for their well thought out plan and exciting research and their presentations. And also I want to thank all the participants. I noticed that when I started my speech probably the least interesting one, or probably the boring part. I counted there were 92 participants. When we get to the highlight at 10 o'clock, we had 157 participants. Now we're at 125. So overall, we have a consistent attention from our participants, which is very interesting to see. Again, I look forward to working with all of you, and thank you all very much again. Okay, Liwen, back to you, Liwen.
All right, thank you again, Professor Song. So any further comment from the unit head and the speakers?
Can I say something?
Sure, KB.
Okay, so probably Liwen, thanks for your very good demonstration. It can be done in a Zoom. So probably you are aware that our school was actually hesitant. We also want to have a school research day. Okay, but we were kind of hesitated whether we should do it in person or do it in Zoom. I think you did a very great example that we can do it in Zoom. Okay, so in this case,
also save money.
Save money.
Yeah. Food.
Yeah. So since all the unit head and all the colleagues are actually here, may I? Okay. So then probably I will proceed to do a research day maybe in the first term. So may I hear, or actually after we got a speaker list, okay, then I will send the invitation to all the members within the Faculty of Science, especially all the unit heads and all and Dean Song, and then to see if you want to join us. Okay, now the research day on the school will be a bit more focused on biological problem. And then I think will be also a good chance to recruit more people to join us in applying bigger grant like Dean Base and CRF. Okay, so here I would like to extend our invitation first. Okay, thank you.
Thank you, KB. Any other comments? I understand that there should be some postgrad students who are also taking part of our research day. Yeah, some of the year 1 or year 2 PhD students, at least from our school. Yeah. So any further comment from speakers, unit heads? One more thing would like that originally also invited our new PVC on research, Maya, to join. She was happy to promise to join us, but suddenly she says there's some engagement at the top level, so she just yeah. Any other further comments? If not, thank you again for a wonderful research day. So we stay tuned for the next one. Okay, thank you again. Okay, bye.
Bye, everyone.
Bye. Bye. Bye.
Bye.